The graph of a linear equation in 3 variables is a plane in 3-dimensional space. You can imagine a plane to be like a sheet of paper that the graphs of 3 such equations that form a system are 3 planes whose intersection determines the number of solutions of the system, as shown in the diagrams at right. Just like the solution of a 2-variable system is an ordered pair, the solution of a 3-variable system is an ordered triple. We can see at right that exactly one solution shows the planes intersect at a single point. To visualize infinitely many solutions, the planes intersect in a line. Every point on the line is a solution of the system, so you can still write your solution in a general form. And here are the options for no solution. There are no points in common with all 3 planes. So some of the planes may have lines in common, but not all 3. Or they could all be parallel planes. To solve a system in 3 variables, rewrite the system as 2 two-variable equations by substitution or elimination. Elimination is far easier than substitution. Use equations 4 and 5 to solve for 1 variable by substitution or elimination. Plug in the value into one of your 2-variable equations to solve for a second variable. Then plug those in to solve for the third in one of the original equations. To determine which variable I'm going to eliminate, I want to look for the least common multiple between the coefficients. What's the smallest number that all of them go into? The coefficients of x all go into 12. The coefficients of y all go into 6. The coefficients of z have a least common multiple of 60. Because the coefficients of the y's have the smallest least common multiple, I will eliminate the y's first. First, I'll eliminate the y's from equations 1 and 3. To do this, I need to multiply the third equation by a scalar to make the coefficient of y -2, so the y's eliminate. Because the coefficient of y is -1, I will just multiply equation 3 by 2. Now add to eliminate the y's. We will call this equation 4. Now it's time to eliminate the y's again using a different pair of equations. Because equation 3 has a coefficient of -1, which is really easy to multiply, we will now eliminate the y's using equations 2 and 3. Using equations 2 and 3, we'll now need to multiply equation 3 by -3, so the coefficient is +3, and we'll eliminate when we add the 2 equations. Now add. This we will label as equation 5. Now that we've eliminated y to create 2 equations with the same 2 variables, x and z, let's use elimination to solve for one of those 2 variables. Often you'll need to multiply by another scalar, but in this case we have opposite coefficients for the x, so we can simply add the equations as they are. Now we can solve for z, and z equals 2. Plug in 2 to either equation 4 or 5 to solve for x. Now that we have values for both z and x, plug those into any of the original 3 equations in order to solve for y. Now that we've solved for all 3 variables, we have our ordered triple. This is in the order x, y, z. But before we box that in or highlight it, let's check to see if this point is truly the solution for this system of 3 variable equations. Because this ordered triple proves all three equations true, this is our solution to this three-variable system. I notice that the coefficients of all the z's are 1 or -1, which is super convenient. So I'm going to first eliminate the z's from equations 1 and 2, and then equations 2 and 3. These two variable equations are now equations 4 and 5. I see that I can multiply equation 4 by -3, and that will eliminate, both the x's and the y's. Let's try it. Zero plus 0 equals 0. So anytime all your variables eliminate, you either have infinitely many solutions in the form of a line or no solution, depending on whether the statement is true. Is 0 equal to 0? Yes, then we have infinitely many solutions. So let's write our solution in general form in terms of x. To write your ordered triple in terms of x, the solution for x would be the variable x. To write y in terms of x, I'm going to take either equation 4 or 5 and solve it for y. I'll take equation 4. So in terms of x, y is equal to x plus 3. Now plug that expression for y into any of the first three equations to solve for z. I'll use equation 1. To write z in terms of x, solve for z. And z is equal to 0. With this general ordered triple, given any value of x, you could find the corresponding y and z to that particular solution point. An amphitheater charges $75 for each seat in section A, $55 for each seat in section B, and $30 for each lawn seat. There are 3 times as many seats in section B as in section A. The revenue from selling all 23,000 seats is $870,000. How many seats are in each section of the amphitheater? I'm going to use the variables A, B, and C to represent section A, section B, and the lawn section. And then write as many relationships that this word problem tells me. First, I'm going to write an equation representing the total number of seats. The seats in section A, section B, and section C add up to a total of 23,000 seats. Now I'm going to write an equation relating the cost of each seat to the total cost. Section A costs $75, so $75 for however many tickets would be 75 times A. 55 per ticket in section B, and 30 per lawn seat. The total revenue was $870,000. There's one other relationship they gave me. There are 3 times as many seats in section B as in section A. So section B has 3 times the amount of tickets as section A. Because B is equal to 3A, I can eliminate B from the other 2 equations by just substituting in 3A and simplifying. Let's multiply equation 4 by the scalar -30 to eliminate the c variable. there are 1,500 seats in section A, and B has 3 times that many, section B will have 4,500 seats. Now plug those values into equation 1 to solve for the number of lawn seats. Since this is just a practice problem, I recommend using a calculator to check your answer, but make sure you know how to do the check so that you can confirm you got the right answer when you're taking an assessment. So the amphitheater has 1,500 seats in section A, 4,500 seats in section B, and 17,000 lawn seats.